Okay, so when you want to check conditions for an ANOVA test, you actually want to check the conditions before the test, but we want to get through the actual conducting of the test before we check conditions. And I just want to remind you that most of these things our guru is going to do for us, just like all the other hypothesis tests that we've done so far. So if you think there's a particular test you want to conduct, you want to make sure that you do verify conditions, but you can conduct the test and our guru to actually verify those conditions. Like I said, in the next video, we'll look at our guru in a little bit more depth to see how they're verified. Okay, so we're still going to be using our original research question of the difference of aldrin concentration in the river at different levels of the river. So, does the condition of independence appear to be satisfied? And in this study, we have no reason to believe the aldrin concentration won't be independent of each other. So this one, like it said earlier, it can be a little difficult to verify. The sample sizes are relatively small at each level. They're 10, and they're not paired. So whatever I capture at the surface is not going to affect what I capture at the bottom. So we have no reason to believe that they aren't independent and they cannot be paired. So we can move on to normality. And so what we are given here are the normal QQ plots of each level along with their histograms to look for any outliers. And so if we look at the normal QQ plots, it looks relatively normal and close, except for surface, there might be some extra variability there. And if we look at the histograms for the same, there's no real clear outliers. And I just want to point out again, you might be tempted to say there's an outlier because there are gaps here, but those gaps are relatively small if we actually look at the x-axis. So 4 to 5.5, we're looking at probably 4.5 here and then 4.5 to 5 here. So really, there's not that big of a gap. And the same thing here, 5 to 7, this is probably 5 to 5.5, 5.5 to 6, 6 to 6.5. So, just missing maybe like one value is not that extreme. And we could also look at the standard deviations to see that that difference is smaller than each standard deviation, which is zero point 0.6 or above. Okay, so for this, we would say there's no clear outliers. Therefore, it's approximately normal. But we're going to keep an eye out on this guy. This might cause some issues for us. Now, finally, we want constant variance. And does this condition appear to be satisfied? And so we're given three different box plots. And this is actually something you should probably start with when you have different categories and you're looking for their mean values to see if there is something worth testing an ANOVA for. So what we have here is the medians. And I would say the bottom and the mid depth, they're, kind of close, but the surface is definitely causing some concern, and its variability is definitely different than mid depth and bottom. So mid depth is 1.6-ish. Sorry, bottom is 1.6-ish, mid depth is 1.1, and surface is 0.6. So things that have constant, the same equal variances, distributions that have equal variances, are said to be homoscedastic. And so that's what we're looking for here is homoscedasticity. And so the two ways you want to verify that is by looking at their box plots and also looking at summary stats, because you want to look at those standard deviations or the variances to compare them. Okay, so we already confirmed that we're going to do the test. We did the test. We found in the previous video that we rejected the null, and there was evidence that at least one of the means was different. The question is which one differs, and ANOVA won't tell you that. You have to do a pairwise t-test. So earlier we concluded that at least one pair of means differ. The natural question that follows is which ones? We can do two sample t-tests for differences in each possible pair of groups. But can you see any pitfalls with this approach? If we run too many tests, the type 1 error rate increases. This issue is resolved by using a modified significance level. So when we're doing multiple comparisons, the scenario of testing many pairs of groups is called multiple comparisons. The Bonferroni correction suggests that more stringent significance level is more appropriate for these tests. So our alpha star is going to be our new significance level for our multiple comparisons. And what we do is we take our old alpha that we did our ANOVA at, and we divide it by our number of categories. So if there are K groups, then usually all possible pairs are compared, and K equals K times K minus 1 divided by 2. And the Aldrin dataset depth has 3 levels: bottom, mid-depth, and surface. If alpha equals 0.05, what should be the modified significance level for 2-sample t-test for determining which pairs of groups have significantly different means? So, okay, K is the number of comparisons being considered. So to find K, our capital K, we're going to take our categories times categories minus 1 and divide by 2. So 3 times 2 divided by 2 is 3. So we'll be conducting 3 different tests. And then our new correction, our Bonferroni correction to our significance level will be taking our original significance level, dividing it by 3. And so our new alpha of concern is 0.0167. So based on the box plots below, which means would you expect to be significantly different? So there's going to be at least 3 tests, right? Bottom versus mid-depth, bottom versus surface, mid-depth versus surface. So the question is, which means would you expect to be significantly different? So I'm going to let you think about that for a second, and then we'll conduct a couple tests to see what we end up with. So we have bottom versus mid-depth, mid-depth versus surface, and bottom versus surface. My hypothesis is that surface and bottom are going to be significantly different, but bottom and mid-depth, not so much, and mid-depth and surface, maybe. If the ANOVA assumption of equal variability across groups is satisfied, then we can use the data from all groups to estimate variability. So estimate any within group standard deviation with the square root of the mean squared error, which we then call our S pooled. We use the error degrees of freedom, which is our sample minus our category for t distributions. Then the difference in 2 means after ANOVA becomes the pooled, which is mean squared error over N1 and mean squared error over N2, which are both 10 in this case because all samples are equal. So is there a difference between the average Aldrin concentration at the bottom and at mid-depth? So this is a 2 population T test. And we still find our test statistic in a similar fashion, but this time because we've already conducted an ANOVA, we use our within group standard deviation as our S pooled, our sample standard deviation pooled. So our T value with 27 degrees of freedom, the degrees of freedom of the error, is the mean at the bottom, which is 6.04, minus the mean at mid-depth, which is 5.05, divided by our mean squared error, which is 1.38, divided by 10, the sample size of the bottom, plus 1.38, divided by the sample size of mid-depth, which happens to be 10 as well, and our t-score is 1.87. The p-value for this, if we look at our student t distribution, is 0.0724. And remember, our corrected significance level, our Bonferroni correction, is 0.0167. So our p-value is actually larger than our significance level, so we fail to reject. The data do not provide convincing evidence of a difference between the average Aldrin concentration at the bottom and at mid-depth, which kind of supports the theory that was stated by looking at the box plot, but we don't ever want to take our visual or summary stats as our conclusive comparison. So let's do one more comparison. This time we'll be looking at the difference in Aldrin concentration at the bottom and at surface. Okay, so we have our summary stats up here. So we're still looking at bottom and surface, and we'll still be using our mean squared error and our residual. So the only thing that's really going to change this time is this value. Okay, so our t-score is still with 27 degrees of freedom. The mean aldrin concentration at the bottom was 6.04, and at the surface it was 4.2. And our sample standard deviation pooled is still going to be our 1.38 divided by 10 plus 1.38 divided by 10. And this gives us a t-score of 3.47. And so if you use the student t-distribution to find your p-value, it's 0.002, and our corrected alpha is 0.0167. And so this time our p-value is less than our significance level, so we reject the null. And we conclude the data do provide convincing evidence of a difference between average aldrin concentration at the bottom and at the surface, which again does support my hypothesis that there was a difference by looking at the box plot. So again, the only thing I can say wrapping this up is that exploratory data analysis is one of the most compelling pieces of work that you could provide when you are deciding to explore a research question. It really should be this exploratory data analysis that's leading the questions you're asking, not you asking the question and having the data tell the story you want to tell. You want to collect data about something and then look at every appropriate graph you can to decide which test should follow. Okay, in the next video, we will look at the output from an ANOVA test on our guru.